This video is part 3 of the lecture on the basic model of multiple linear regression. Multivariate analysis can help us to investigate relationships among 3 or more variables in various ways, and one of the most important among them is control of confounding factors. Suppose that we are interested in a variable and there are a number of factors that may affect the variable of interest. Then, we can look at the statistical relation between the variable of interest and each of its factors, one by one. That will be a set of separate bivariate analyses. Isn't such a set of bivariate analyses enough? Why do we need to analyze effects of multiple factors together? Suppose we focus on one of the factors, so we want to study relationship between the factor, let's denote it as x, and the variable of interest, let's denote it as y. We want to study the relationships between x and y, independently of effects of other factors. For example, suppose we are doing some pharmacological research, and we are interested in effects of a medication on some physiological condition. So we may get a number of study participants, split them into 2 groups, and give the medication to one of the 2 groups, and a placebo, which looks like a medication but has nothing special, to the other group. We may call the first group the experimental group, and the second group the control group. Then, we may want to follow the physiological condition of those in the experimental and control groups through the experiment. But suppose people in the experimental group are mostly women, and people in the control group are mostly men. Then, differences between the 2 groups may reflect both effects of the medication and gender differences in the physiological condition. Or suppose people in the experimental group are mostly old persons and those in the control group of mostly young persons. Then, observed physiological differences between the 2 groups may reflect both effects of the medication and age differences in the physiological condition. Other characteristics may matter. What if those in the experimental group are mostly smokers, and those in the control group are non-smokers? In these cases, effects of the medication may be statistically confounded by some other factors, such as gender, age, smoking, etc. How do we control those confounding factors in experimental research? Usually 2 methods are used together. One is blocking or block design. For example, if the study participants include 8 women in the 40s, we assign 4 of them to the experimental group, and the other 4 to the control group. In this way, we can make the 2 groups have similar compositions, in terms of some important identifiable characteristics such as gender and age. Then, instead of letting those women choose their group by themselves, we randomly assign 4 of them to the experimental group, and the other 4 to the control group. Since we don't know every characteristic of the study participants, we cannot make the 2 groups similar with respect to those unknown characteristics, but we expect that this random assignment will reduce the risk of having a very uneven distribution of some characteristics between the 2 groups. Blocking and randomization are useful tools for controlling confounding factors in experimental research. But in many cases, experimental control is ethically, technically, or financially impossible or difficult. For example, suppose we are doing a study on health outcomes of cigarette smoking. But since many detrimental effects of smoking on health have already been found, we should not and cannot ask a group of people to smoke cigarettes for the next few years. So we have to depend on observational research, in such a case. Data from those who smoke and those who do not smoke are collected and health conditions of the 2 groups are compared. But smokers and non-smokers probably have different distributions with respect to some characteristics, which may have some health effects. So in observational research, it is important to control confounding factors. In observational research, since we cannot use experimental control, we control confounding factors by statistical manipulation of data, such as multiple linear regression. Usually it is not as effective as experimental control, but still it helps. In this section, we briefly go through a research paper, which is a reading assignment for this session. The authors, Hall and Greendale, provide us with a typical example of use of multiple linear regression in health research. The researchers are concerned about osteoporosis, which is a serious health problem in the aging society. In many old persons, particularly in old women, bone density tends to decline with age, raising the risk of fracture and other health problems. The authors are pursuing prevention of osteoporosis by dietary means, and have hypothesized that vitamin C consumption should raise bone density and reduce the risk of osteoporosis. So they investigated the relationships between bone mineral density, here abbreviated as BMD, and factors, including vitamin C consumption, that may affect bone density. Since bone density is a numerical variable, measured in grams per centimeter squared, multiple linear regression is considered a suitable tool for this research question. The dependent variable of this regression analysis is bone density, which is not one variable, because bone density can be measured at different sites in the body. In this study, bone density was measured at 3 sites: the femoral neck, hip, and spine. The femoral neck is the top of the bone of the leg between the pelvis and knee. This analysis included vitamin C consumption and some other variables, which are considered to be possible determinants of bone density. The data were collected from 775 postmenopausal women between 45 and 64 of age. The researchers adopted 3 different regression models for each of the 3 sites, shown in the leftmost column of this table. So in total, 9 regression analyses were done. The results are summarized in this table. The column titled Predictor Variables, showing dependent variables of each regression analysis. As shown there, all of the models included vitamin C as an independent variable. The column titled Beta Coefficient displays the estimated values of the regression coefficient for vitamin C. The rightmost columns show p-value and r-squared, which we will study in sessions 5 and 4. As shown in this slide, first, they did simple linear regression of bone density on vitamin C only, and then regression on vitamin C, age, and BMI together, and finally they included all of those 8 factors. Estimated values of regression coefficient for vitamin C from regression of bone density at the femoral neck are shown here: 0.015, 0.018, and 0.017. The unit of analysis of vitamin C consumption is 100 mg per day. So, 0.015 means an increase in bone density by 0.015 gram per squared centimeter, corresponds to an increase of daily consumption of vitamin C by 100 mg. Considering the units of bone density and vitamin C used in this analysis, these values do not seem to indicate very strong effects. But these values are all positive, which means, women who consume more vitamin C tend to have higher levels of bone density at the femoral neck. These values are statistically significant, according to the regular standards. So it can be considered that the results are consistent with the hypothesis of the researchers, i.e., vitamin C consumption has positive effect on the bone density of postmenopausal women. The 3 regression models are shown here in the equation form. A is the constant, Vc is vitamin C consumption, and B1 is the regression coefficient for vitamin C. For bone density at the femoral neck, the value of B1 changed from 0.015 to 0.018 and to 0.017. So the value of B1 did not change very much when more factors were added to the model. This may suggest that vitamin C consumption may not be strongly correlated with those factors. Let's look at another example, which is actually the software example for this session. I recommend that you view this section after going through the software example. In this data, the unit of analysis is not a person but a U.S. state. The dataset consists of 5 variables for 50 U.S. states and the District of Columbia. The names of the 5 variables are not healthy, obesity, high school, smoking, and insurance. Not healthy is the percent of adults in the state who reported their health condition as fair or poor instead of excellent, very good, or good. Obesity is the percent of adults whose BMI is 30 or over. High school is the percent of adults who have completed high school education. Smoking is the percent of adults who are currently smoking. And insurance is the percent of adults who are not covered by health insurance. The data sources are BRFSS, Behavioral Risk Factor Surveillance System, and census-based estimates. Values for those variables indicate conditions at some time between year 2003 and 2005. We examined whether states that have higher proportions of obese adults tend to have higher proportions of adults who are self-reportedly unhealthy. It should be noted that, since this is aggregated level data, not individual level data, we did not examine whether obese adults tend to be self-reportedly unhealthy. That research question should be investigated with individual level data. First, we did simple linear regression of not healthy on obesity, and then multiple linear regression of not healthy on obesity, high school, smoking, and insurance, together. The estimated regression equations are shown here. The coefficient for obesity in the simple regression was 0.76. It means that, the typical pattern of relation between obesity and not healthy in the data is, if the proportion of adults who are obese increases by 1 percentage point, then the proportion not being healthy increases by 0.76 percentage point. If we prefer to use larger numbers, we can also say, if the proportion of adults who are obese increases by 10 percentage point, then the proportion of adults not being healthy being self-reportedly unhealthy increases 7.6 percentage points. This seems a fairly strong relation. However, both of these two variables are correlated with the other three variables. Multiple linear regression incorporated the information on these correlations, and makes it possible to estimate what the relation between not healthy and obesity would be, if we could compare U.S. states that have the same proportion of adults who have graduated from high school, the same proportion of adults as who are currently smoking, and the same proportion of adults who are not covered by health insurance. It was estimated that, in the hypothetical situation, if the proportion of adults who are obese increases by 10 percentage points, then the proportion of adults who are self-reportedly unhealthy increases by about 2.4 percentage points. This is what the estimated value of partial regression coefficient for obesity, 0.24, means. The regression results can be represented schematically, as in the next two slides. The coefficient for obesity in the simple regression was 0.76. This value represents the typical pattern of relation between not healthy and obesity, thereby summarizing the association between the two variables in the data. With three additional variables, high school, smoking, and insurance, the association between not healthy and obesity can be decomposed into four components: the association between not healthy and obesity through their relations to high school, the association between not healthy and obesity through their relations to smoking, the association between not healthy and obesity through their relations to insurance, and the association between not healthy and obesity controlling for high school, smoking, and insurance, i.e., what the association between not healthy and obesity would be, if they are compared among U.S. states that have the same values for high school, smoking, and insurance. This slide shows results of the decomposition using a method called path analysis. Through high school, an increase in not healthy by 0.346 percentage points corresponds to 1 percentage point increase in obesity. Through smoking, an increase in not healthy by 0.062 percentage points corresponds to 1 percentage point increase in obesity. Through insurance, an increase in not healthy by 0.114 percentage points corresponds to 1 percentage point increase in obesity. And if we compare not healthy and obesity among U.S. states that have the same values for high school, smoking, and insurance, then we would find that an increase in not healthy by 0.237 percentage points corresponds to 1 percentage point increase in obesity. And in total, an increase in not healthy by 0.759 percentage points corresponds to 1 percentage point increase in obesity. Note that these four numbers, 0.346, 0.062, 0.114, and 0.237, add up to 0.759. This is a plot of not healthy by obesity, i.e., the percent of adults who are self-reportedly unhealthy, by the percent of adults who are obese, in the original data. Each circle represents a U.S. state or DC. The red line is the regression model fitted to this data, and its slope is 0.759, meaning the typical pattern of association between the two variables is, an increase in not healthy by 0.759 percentage point, corresponds to 1 percentage point increase in obesity. This plot shows what the relation between not healthy and obesity would look like, if 50 U.S. states and DC had the same proportions of adults who have graduated from high school, who are currently smoking, and who are not covered by health insurance. In a later session of this course, we will study how to produce this plot, but it will be close to the end of the course. This is not original data themselves, but a hypothetical pattern which was estimated by fitting the multiple linear regression model to the data. The slope of the regression line is now 0.237, which is less steep than the slope of the regression line in the previous slide. The association between the two variables appeared stronger in the previous slide, but the differences between the two plots are due to the fact that both of them are associated with high school, smoking, and insurance. Next week we will talk about how to use and interpret categorical variables in a linear regression.